try to send this. Yes. Yes. No, but we do have the other, add and subtract instructions.
You need to install your fonts.
Huh?
You need to install some more fonts.
Well, I used to use, I lost my settings, so that's why I kind
Well, look at your next and up and previous and contents buttons.
All right, well, let's go ahead and get started, because depending on how much stuff we can cover today, I can decide, what your next homework assignment is going to be.
Can you just give us add and subtract CL and make us add and subtract really big numbers?
Okay, let's go ahead and get started. Last time we talked about unconditional jumps already. Basically, it's just a go-to. You specify the label to continue execution, and it will continue execution at the label. That's unconditional jumps. And then we talked about conditional jumps, which are basically the first instructions that will make use of all the flags that we have talked about so far. Okay, so I'll just kind of go back to that slide to talk about these instructions. This is basically what we talked about last time. A conditional branch instruction, just like JC in this case, is going to jump to the label that you specify if and only if the carry flag is a 1. Okay? So that means if the carry flag is a 0, it will just continue execution with the instruction following the JC instruction. So that's how the conditional branch works. It's basically the same thing as a go-to, or a conditional statement with a go-to, but there's no else. The else is just, whatever is next to the statement itself. So let me just, use a text editor to write what I said so that it has a, textual representation. So JC to, say, L1 is basically equivalent to if carry flag is a 1. Now, I know that is completely redundant, but, there you go. Or you can say when it is not 0. That's a better way to say it because true is not necessarily 1 in C. It's just non-zero. So if C is non-zero, go to label L1, and that's it. That's the same thing as a JC L1.
Let's do the semicolon.
Oh, sure. I can put the semicolon here, right?
Sure.
It's C.
You can put the semicolon 3 lines and 7 comments later.
And I can make it so that it has its own little scope,
You can put a scope within a scope.
Yep. But that's basically what it is. A conditional branch is just that. Okay? So if the carry flag is non-zero, if the carry flag is 0 or false, it would just execute whatever statement is after the conditional statement. If it is non-zero, it would just go to the label L1, wherever label L1 is. Are we doing okay so far with the concept of a conditional branch instruction? And I think last time we went through a certain example program to illustrate the concept of conditional branches. Is that right? Let's go ahead and do it. Okay, so today what we'll do is we'll start with a program, and we'll have our first loop. Okay, we did a loop last time. We did an infinite loop last time. Basically a branch back to underscore start. So what we'll do today is to do a countdown loop to do something along this line. Okay, so we'll say, while x is less than 3, do, okay, never mind, this is C and not a pseudocode. And, or something like that. Yes? Make the font a little bit bigger.
You could do that.
Yes, I can do a lot of stuff. There we go. Okay, So let's go ahead and try to see what we can do to translate this into regular assembly language code. Yep.
Can we have it print out the number as it goes through the loop as well? That sounds fine.
No. Because the debugger can do that. We can stop at the label and then we can print out the value of x whenever it gets there. Okay. So how do we go about doing this? This is a while loop. It has a condition. If the condition is true, we stay in the loop. Okay. So given all the instructions that we have dealt with at this point, let me just make this a little bit easier so we can say unsigned long x. Okay. Which means x is a 32-bit integer. Okay. Yep.
Did you mean x is greater than 2? I was going to say that's going to go on.
It's an infinite loop, huh?
Yeah.
Or I can change
You need
this
int x equals 3.
initialization.
And you need to initialize. There you go.
Okay. All right. Minor details. The question is, can you translate it, not what it is going to do. So if it is an infinite loop, so be it.
We did that exactly. We
Yes.
did that.
Well, it won't be an infinite loop, would it? Because it will just go all the way around, and then at some point it will be less than 3. Right? Yeah. So it won't be an infinite loop for long. Okay? It will always get out. Okay. So we have this particular program here in C, and we want to see how to translate that into assembly code. So what we'll do is we'll start another editor to deal with that part. So let's go ahead and save this into today's folder first, before I forget. And we'll go ahead and display that side by side. Go to today's folder, 0308. How should we call this loop? Change the font. That's mighty big. Okay. There we go. So we can now see both the C code and also the assembly code at the same time. The data section is fairly simple. Okay, the data section only needs to declare the storage space for our variable x. In this case, a .int would do the trick. I have to give it a label, x.int 0. So this means this is basically the same thing as unsigned long int, and then we have an equal 0 here because we are both allocating the space and also initializing it to 0 at the same time. And then we can start with the code section in .text. So we have the usual stuff, okay, global _ start to export the label _ start so that the linker can do its job and identify where is the entry point of the program. And then we can start the label, define the start label. The first thing we want to do is to initialize x. In other words, we want to perform this operation here. So the one way you can do, one thing you can do to help remind you, which part of the program you're dealing with, is to use comments, to identify what you're trying to do in C, pseudocode, or some other programming language, and then put your assembly code immediately below that. So that way you can basically just look at the comments and understand what you're trying to do in assembly. So the first thing we want to do is to initialize x to 0. So can anyone tell me how this is done?
It's already done.
Move L 0i.
Yep. Okay, move L, $, okay, very important. Without the $sign, the program will give you a general protection fault. Yep.
Didn't you already do that though?
Sorry?
Isn't that already done?
Yeah, it is, but since, I have this in the code already, I will do it also, at runtime. If you do it over here, it will only be done one time. Okay, when the program is loaded, that's the only time x is guaranteed to have a value of 0. If you do it in the code, then you make sure that the program, by the time it gets to that point of the program, it will always start with a value of 0. So that takes care of that. So the next one we want to do is, how do we do the while x is less than 3? and later on, we have some additional code. Okay, so this is the part where it's a little bit counterintuitive. When you look at the C code, it specifies the condition when you stay in the loop. But when you program this thing in assembly language, it is easier to think of the condition to get out of the loop. Okay. So what we want to do first, okay, so let me just kind of go back to the C code first. And what I'm doing here is, to make this program really ugly. I'm staying within C, but I'm turning a structured C program without any go-tos into a program that uses go-tos. Okay. If I'm going to turn this program, or particularly this part here, into C code that will use a conditional statement and a go-to, but without the while, how will I go about doing it? I don't want to do it 3 times, because the comparison here may compare to y, then I cannot know ahead of time how many times I want to do it. So I still want to do something like this. How about something like this? If x is greater than or equal to 3, go to a label that I call L1. Otherwise, we perform the operation, which is x plus equal 1, and then we specify. Okay, they are at exactly the same level, so the indentation was wrong originally. So we have to go back to L0, and I have to define L0 here because I have to reevaluate the condition after every single iteration. And then L1 is effectively the exit label, so that goes after the go-to because it is after the while loop. So let's just go ahead and double check and see whether this logic here, not the initialization, not counting the initialization, just the loop itself, and double check that this logic here is captured by the rather ugly and taboo C code, but hopefully it is functionally the same. Are they functionally the same?
Should be.
Take a look. Yep, go ahead.
Can you have only one go-to statement by just having it at the end of the x plus 1, and then once the condition is solved, it'll just keep executing? Like, could you only have one go-to statement instead of 2?
Yes. If you want to have only one go-to statement, you can only do it if you have a do-while loop. A do-while loop only has one conditional statement because you specify when to get back to the beginning. But when you deal with a while loop, you always have 2 go-tos because there are 2 branches here. One branch is from here to get out of the loop. The other branch is after you perform the operation, you have to go back to the beginning. So you can't really get around the 2 go-to problem with a while loop. If you can turn a while loop into a do-while loop, then you can have only one single go-to, to implement the loop. Okay. So is everybody convinced that this is a uglier, but otherwise functionally the same as the while loop itself? The next step is to take a look at this code here and say, well, can we turn this into assembly code? This is when we look into here and say, can we turn that piece of code here into assembly code? So instead of putting this code here, let's try and put the C code of L0 here. Can I define a label L0 in assembly?
Sure.
What is the syntax to do that?
L0 colon.
Exactly the same thing. Okay. Now, when you do something like this, using a label name like L0, L1, may not be the best thing. Yep. Go ahead.
Can you do the L0 in C?
Yes.
Is that valid syntax?
Yes, it is.
Oh. We
Yep.
learned something new in C today.
It is just a taboo, and that's why neither Iraj or Damon would mention anything about that. But since this class is about low-level programming, so we don't have any such thing as taboo in this class.
Go-to is used to implement all the structures.
Hmm?
Go-to is used to implement all the
Yep,
structures.
that's the only thing we have. Well, other than call and return, which can also be done by go-tos. Okay, so L0 is just L0. It is better to call these labels like loop begin and loop end, if you're actually writing the program. But for now,
Okay,
I'm
let's
just
do
sticking
that.
with L0 and L1. And L0, that's fine, that's the easy part. What about this part here? If x is greater than or equal to 3, go to L1. How do we translate that into assembly language? I know we cannot do it in one single on one single line or in one single instruction. We have to break it up into 2 instructions. Okay, so since I already know we have to break it up into two instructions, I know the first instruction is going to be a compare long because x is an unsigned long integer, a 32-bit integer. Okay, and since I have a constant 3, I will put the 3 here, and I have the direct operand x, I will put it here. The other question is, what am I going to do here? Is to say jump to L1. This is the question. Okay, what do I put next to the j? Now you have to remember how to read something, because I want this to do, if x is greater than or equal to 3, go to L1. So here we say jump if x is
0.
greater than or equal to or not less than, but not less than in unsigned is not below. J and B. That would do the trick. Okay, so any questions about this part? Well, let's take a look, and see, break down each instruction in assembly and see what it is really doing. The first instruction, which is the compare long instruction, let me turn on line numbers so we can refer to line numbers instead. And we can also turn on syntax highlighting. Okay, so let's take a look at line 11 first. Line 11 is compare long $3x. In other words, we are actually basically performing a subtraction operation, except we don't store the result back into x. The subtraction is x minus 3. Okay, we are subtracting 3 from x. Then we look at the result of that subtraction and say, if there's no borrow when we subtract 3 from x, go to label L1. Is that really doing the same thing as going to L1 if and only if x is greater than or equal to 3? It is. Okay. So it might take a little bit of time for you guys to kind of get used to the ordering of things, because when you read this code here, read this part here, the proper way to read it is jump to L1 if and only if x is not below 3. That's the way to read it. Yep.
I had a quick question. I think you already mentioned this. If we have like a ton of jump commands, when do the flags get changed again?
The flags are only affected by add, subtract, compare, multiply, divide, and most of the arithmetic operations.
Okay, so if we had like J and B going to something else, and they're all just jump commands, the flags actually wouldn't get changed?
They would not get changed. Yep. Yep.
Can you replace both of those commands with the JZ?
Yes, in this case you can replace it with a JZ, but the JZ is dangerous because it is not truly equivalent to greater than or equal to. If you replace that with a JZ, then if I change the initialization here to say 5, then it won't work. Do you see what I mean?
Yeah.
So in this specific case, if I start x off with a value that is less than or equal to 3, then you can replace J and B with just JZ. That will work. But if I change the initialization here to say a 5 or a 6 or anything that is greater than 3, then the JZ would not work anymore, because then you will have to wait until it goes all the way around to become 3 again. Good question, though. Yep.
Can you say again how you would translate that into words where you said
Sure. Okay, so
jump
the
to L1 if and only if?
Yep. So the way to read this, you have to kind of practice it a few times to really get used to the pattern. So it is jump to L1 if and only if x is not below 3. So there's a kind of like a specific order to read this thing. Once you do it enough times, you will start to recognize it. I would say getting used to this is a little bit faster than learning hexadecimal digits. Yep. So you start with a jump, and then the label, jump to the label L1, if and only if. The really tricky part is when you read the two operands of the compare, you have to read the second operand first. That is the key. Okay, so in this case, x is not below 3. Okay, any questions about this one? Okay, if there are no questions about this one, we'll continue with the C code. The next line of C code is x plus equal 1, semicolon, and we can do this pretty easily in assembly. How do we do it? Add long. $1. Very good. Okay, so you got to make sure that you make the distinction between a direct operand and an immediate operand, because syntactically speaking, they look very similar, but in terms of behavior, they're completely different. It's not really the worst kind of mistake you can make, because if you did make a mistake here, your program will crash on this single instruction. And when you look at the instruction, you look at it and you can almost tell right away what the problem is. The worst kind of mistake is when you corrupt something else that you're not using right away. Then the symptom will only show up much later, and it's much more difficult to make the association at the time the program breaks to where the problem really is. Okay, so we'll see those problems later on when we have subroutines and other stuff. Okay. And now we have go to L0 as my C code. Do we have anything that can do the same thing in assembly?
Jump L0.
Just an unconditional jump to L0. That's good. And then in C code, we have the definition of label L1. Can we do the same thing in assembly?
Yeah.
Okay, exactly the same thing. So technically speaking, we are done with the translation from C code on this side here to the assembly code on this side.
Except that we've got extra in the assembly that we need to finish out.
What?
We've got extra in the assembly, the header. We omitted that in the C side, so we need to finish that at the bottom.
Finish what?
Int 80.
Yeah, exit code.
Yeah.
Yeah. The exit code is always going to be there, just so that the program will exit correctly. Like that. And if I want to specify what this is really doing, it is doing that in assembly code. It's equivalent to exit 0 in C. Yep.
So what tells it 0? What does the 1 and the
EBX.
0 mean?
The 1 is system surface number 1, which is exit. The 0 is the value in EBX. If you want to exit with a code of, say, 5, you can just put a 5 into EBX, and the program will exit with a code of 5. So that's how you control the exit code.
So what is interrupt 0x80?
That's the single vector, software interrupt vector to request surface from the Linux kernel. And that makes the Linux kernel a fairly well-defended kernel, because the interface to the actual kernel is only that small. We'll talk about that in the next 2 topics or so.
Okay.
Questions about this? Nope. Okay, so I'll save it, go back to the command prompt, and actually try to run the program. LD and then GBB. Okay, so we'll list the program, and we'll find a place to put a breakpoint so that we can look at the value of x as x is incremented. Let's put a breakpoint on line 11. Line 11 is our compare instruction. So we'll stop right before the compare so that we can take a look at the value of x before the comparison. And then we can single step the next few steps to see whether it is branching correctly or not. So we'll run the program. This is the first time. If I print the value of x, it is 0. Now, I can do this only because I made x a 32-bit number, and that just kind of matches the misunderstanding of GDB. Okay, if x is a 16-bit number, then it doesn't work out anymore. Okay, it is just because GDB misunderstands everything is a 32-bit integer. So we can now single step. Okay, compare single step. This is right before we do the JNB. I can now take a look at the E flags register. And you can see the borrow flag or the carry flag is set. So are we going to jump to L1? Nope, not going to jump to L1, which means we're continuing with the next instruction, adding 1 to x. And if you're not convinced, we can print x. X has a value of 1 at this point. The unconditional branch instruction will branch us back to label L0, which means we'll compare again. X now has a value of 1. 1 minus 3, will that generate the borrow flag?
Yes.
Okay, so let's double check and confirm that. The borrow flag or the carry flag is turned on, just as expected, no problem. Single step, and then go back to the compare instruction. It is 2 this time. 2 minus 3 will still generate the carry flag. Okay, just to be sure, x now has a value of 2. After the comparison, take a look at the flags. The carry flag is still on. So we are not branching to L1. We will execute the add along instruction. Adding 1 to x, go back to label L0, perform the comparison. This time x has a value of 3. Would 3 minus 3 generate a borrow? No. Nope. So this time, if I look at IRE flags, the borrow flag is off, which means the conditional branch instruction will branch to L1 in this case. So if I single step, you will see that the line number is not consecutive anymore. It is line 12 at this point. When I single step, it jumped all the way to line 20 because this is the line below the definition of the label L1. Okay, so this is a fairly short program, but it does make the point. And and not only that, we also got some kind of insight about how to translate a loop in C into assembly. The general idea, not the exact details. Are there any questions so far about this example? Let me just switch back to the source code here so that people can see the entire program. Any questions about this? No questions? Okay. So if there are no questions, I'll get out of the editor, get out of the debugger, and then go back to our notes here. Now these conditional branch instructions, every single one of these will only take a look at one single flag to determine whether to branch to the label that you specify or not. We have 4 flags, the 4 basic flags, and therefore we have 8 instructions because each flag has 2 instructions. Jump if and only if the carry flag is set. Jump if and only if the carry flag is cleared. So there are 2 instructions per flag in this case. So here we have a little bit of a. Okay, let's combine this with the other ones too. These instructions, okay, if you look at JL, JNL, JG, JNG, JA, and JNA, these instructions do not look at one single flag in order to determine whether it should branch or not. Does that make any sense?
Yeah.
Okay, because is there a real flag called the L flag? No. How do we compute the L flag? O and S, the sign flag and the overflow flag. Okay, and the G, if you say jump if and only if greater than after a signed comparison, this one actually takes a look at 3 flags and not 2, because it also has to take a look at the 0 flag. Okay, is that making any sense? When you want to confirm a number is greater than the other number in signed interpretation, you have to take a look at 3 flags. Okay. And if you look at the flags, JG is basically the same thing as this here. Jump if and only if the 0 flag is 0 and the exclusive OR between the sign and the overflow flag is a 0 as well. Because the 0 flag being 0 means it is not equal. Okay, greater than is not equal to. So that's why I have to rule out the case that the 2 numbers are actually the same as each other. And also, I also have to confirm that the L flag is a 0, but the L flag is just a pretend flag. The actual equation to compute the L flag is the sign flag exclusive or the overflow flag.
Is that a negation over the 0?
No, I don't think so. I think it's just an artifact. Yeah, it's still there.
Or if you try highlighting it, then
Don't you need
Oh,
it?
fine. No, I don't need negation because this one is just confirming the Z flag is a 0. Yep. I think it's an artifact. If I refresh, it's not.
Oh, there you go.
Yeah. Okay. So let's go ahead and do one exercise. Let's just say that we only have conditional branches on simple flags. And not only that, we can only branch on confirming the flag is on. In other words, I'm trying to do everything with JC, JO, JS, and JZ, and the unconditional branch. I have 5 basic instructions. Let's see if I can, come up with the equivalent code to perform the JG instruction. Okay? And this is my own assignment for this class. Okay. So tax assignment to himself. Okay? Pretend that we only have JC, JO, JS, and JZ. Okay, wait, JZ and the regular jump, which is unconditional. Implement JG L1. That's my homework. That's my not homework, in-class assignment. Does everybody understand what I'm trying to do? Okay, so instead of all the compound, jump instructions, I only have the really basic ones. I can only have JC, JO, JS, and JZ, and also the unconditional branch instruction jump. But I want to accomplish the same thing as a JGL1. So the question is, how do I go about doing this? Okay. So I definitely want to define L1 somewhere. Okay, so L1 is defined, down here. I don't care where L1 is defined. It's just somewhere, down there or up there. Doesn't matter where it is defined. What do you think would be a good way to go, since I can only have the positive conditional branches? I will start with the JZ. Okay, I will start with the JZ to the label. I'm trying to think of a label. Okay, continue. Okay, and I'll define the continue label down here. In other words, if the Z flag is on, there's no way one operand is greater than the other operand. So I can basically jump around the rest of this code here and just say continue with whatever instruction is following the JG instruction. Does that make any sense? So that's the easy one, to rule out the two numbers are exactly the same. So the next one I have is basically either JS or JO. I know JC is not going to do me any good, right? Because JG is for signed comparison, and JC is only for unsigned comparison. So I know JC is not going to do me any good. And between the JO and the JS, it's all the same. They're basically symmetric. So I start with the JO. Doesn't matter. And I will go to a label that will identify this is the place to go when the overflow flag is on. Okay. So I will say jump to overflow is on, okay, or the overflow flag is set. And I will define the label right away down here somewhere. Now, this is also a personal habit. When I do conditional branches in assembly programming, I would typically put a line of comment right below the JO instruction to remind myself what does it mean if I continue execution after the JO instruction. Yep.
One F is lowercase, the other F is capitalized.
Oh, okay. Thank you. Overflow is one word, therefore the flow should not be capitalized. Thank you. Okay, so I put a line of comment here to remind myself what does it mean if I get here. If I get here, that means the overflow flag is a 0. If I get here, that means the overflow flag is a 1. Okay, because I will lose track of the flow of the logic really quick if I don't remind myself what does it mean to get to hit this point here. If I know the overflow flag is a 0, and I can only use JS at this point, what do you think I should do about JS? The overflow flag is a 0, the sign flag is on, so should I go to L1 or not?
Yeah.
Continue.
Wait, I'm branching if it is greater than, not less than. Okay, at this point I know the overflow flag is a 0. JS will branch if the sign flag is on. Overflow flag 0, sign flag 1 means the L flag is going to be on, which also means it is not greater than. Okay, so that means I actually have to jump to continue here, But that also means if I continue execution at this point, I just confirm that the overflow flag is a 0 and the sign flag is 0 as well, because otherwise I would not end up here. So this is a good time to jump to label L1. Because when the overflow flag is a 0 and the sign flag is a 0, that means the L flag is off. The L flag is off, which means it is not less than. If it is not 0 and it is not less than, what is the only choice left? It has to be greater than. Okay. So here we have the other part. In here, overflow flag is already set by the time I get to this label, and the next instruction has to be a JS instruction. Remember, I do not have J and S anymore. I can only have the conditional branch when a flag is set. So what should I do here? Which label should I go to? Nope. When the overflow flag is 1 and the sign flag is 1, that means the L flag is off. When the L flag is off, it means it's not less than. But since I already confirmed it is not equal to from the beginning, so that means this is also a good time to go to label L1. And then the continue label will be defined down here. So this is the code. If I did not have JG as one single instruction, this and only have the confirming, conditional branches, this is what I would have to do in order to implement the JG instruction. Are we doing okay in terms of concepts? Okay, the details definitely take some time to get used to, but in terms of the concept, it can be done. It's just a little bit ugly. Okay, it does not really map to anything that you have to do in your cisp310 class, does it? And that's why you see, that's the reason why I label all the lines, right below a conditional branch instruction, as well as the lines right below a label, because I need to remind myself, what does it mean if I get to this part of the program? What does it mean when I get to this part of the program? And so on. Okay. Are there any questions at this point about these conditional branch instructions? Now, this is also interesting because we are looking at things from the RISC perspective, reduced instruction set computers. Because when you want to reduce the number of instructions, then you want to only implement this minimal set. There's nothing smaller than this set here. Okay, and out of these 5 instructions, I can do all the other conditional branch instructions that the Intel processor supports. Now, how many instructions are we talking about here? We are talking about 8 just for the basic flags, and then plus 6 for the compound flags. So we are talking about 8 plus 6 is 14. 14 plus the unconditional branch is 15 instructions. In other words, the Intel processor will give you a choice of 15 instructions, but the 15 instructions can be implemented by only 5 instructions. It is a reduction of 66%. Okay, we are reducing the number of instructions by 2/3 by just going for the most basic conditional branch instructions. And that's the basic idea between, basic difference between the RISC architecture, like the AVR or the ARM architecture, versus the Intel architecture, which is a CISC architecture. Now, as a programmer, which one do you prefer?
RISC.
Okay, but you can also use macros. Okay, most assemblers allow you to use macros. In other words, if you already know the structure of a JG looks like this using the basic instructions, you can actually define a macro to expand the macro into these instructions whenever you specify the JG macro.
Wouldn't this be the same thing?
It will basically mean the same thing.
So why wouldn't you just use a cis?
Because you still want a less expensive processor on your cell phone, and you want your battery to be this small instead of a brick. That's the reason. So are we doing okay in terms of the concepts of conditional branches using flags and stuff like that? Kind of. May not be the details. The details you really have to look at this again just kind of follow each branch. It may be helpful if you make a spreadsheet out of this. Okay, one way to do this is to use a spreadsheet to indicate the line numbers, and then on another column. Okay, so you basically have 3 columns or a few columns. One column for the instructions, one column for the confirmation of the flags. You only have 4 flags in this case, and some of the flags are not important. So you basically just say the Z flag, the overflow flag, and the sign flag as 3 columns. If you don't know anything about the flags, don't say anything. If you can confirm that the flag is a 0, put a 0 there. If you can confirm the flag is a 1, put a 1 there. Okay, so that way you can actually tell by the time we get to L1, what flag combinations can get you to the label L1, and what flag combinations will get you to the label continue, and that will give you a much better understanding of how this code is going to do the same thing as the JG instruction. Okay, any questions about this part? Does everybody understand what I just said, about using a spreadsheet to help you understand at which label or which line, which flag combination you can confirm? Okay, it's a trace, basically, but you're looking at the trace, for every single combination. It's more like a pre and post condition thing from cisp310. It's not really a trace. Okay, so if that is done, yes.
Can you do the same thing with your JNB?
Yeah. The JNB is easy. Okay, so here's the next question. Okay, JNB is really, really easy. Okay, how do we implement JNB L1? What do you think? Well, you just say JC to continue. Whatever is after that, jump to L1, and then you define continue here. So this sequence is equivalent to JNB L1. Basically, I just want to confirm by the time I get to L, I can only get to label L1 if and only if the carry flag is cleared. Okay, will this do that? Yep. I picked a difficult example for myself. Yep.
Now, for the if and only if, you'd have to have some logic in between continue and L1. We're going to continue to flow into L1, right?
It can still fall through, but there has to be some code in between. Yes. Because otherwise, the 2 labels are equivalent. Yep. Any other questions? No other questions. So let's go ahead and go back to the notes so that we know where we stand right now in terms of the notes. We are basically done with jump instructions, and we'll move on to section 5 or topic number 5. I think this semester I'm going a little bit slower, for one reason or another. I'm going a little bit slower because with my cisp310 class, we are starting to talk about subroutines. And in past semesters, these 2 classes, cisp310 and 300, will start to talk about subroutines at about the same time. And this time, P300 is actually a little bit ahead of P310. I think it has to do with the class size, just getting a little bit bigger. Okay, so let's go ahead and talk about control structures. Control structures refer to conditional statements, loops, and stuff like that in C. Now, for the purpose of this class, I will only talk about while loop and also conditional statements. Okay, do while, maybe. I'll talk about do while, and if. I'm not going to talk about for loops. Why not?
They're just like while and by.
It's a while loop, except you specify the precondition or the initialization, you specify the post operation, and then you specify the condition.
It's more convenient while.
It's a very convenient way to look at a fancy while loop, exactly. So let's go ahead and start with this topic. And the topic name is compiling control structures because you are basically doing the job of a compiler by translating high-level control structures into low-level assembly language code. And here we have a really fast refresh of the conditional statements. This is the conditional statement, okay, a general conditional statement. Are there any questions about this part? I mean, BLK1 is block 1, BLK2 is block 2. Block 1 executes if and only if the condition C is true. Block 2 executes if and only if the condition C is false. Okay? Any questions about this part? No? Yep.
What are the conditions?
The condition is C, whatever it is.
Uh,
It is abstract. Because what we're doing is we're trying to translate it into something that does not have else. We want to translate that into something that looks like this and this. Okay? So can someone point out why I'm trying to do this?
Is it easier to go from that to assembly?
Exactly. It is easier to go from here to assembly because if C is just, something is less than something else, I can do it with one compared instruction with a conditional branch instruction. Okay? So that's why I'm trying to break up the program and get rid of the else and get rid of all the structured code that you have come to like in structured programming. So we are doing exactly the opposite of cisp360. We start with something that is structured, we break it apart so it's no longer quote-unquote structured. But the way we break it down is actually structured itself. So the method to break it down is structured, it's just that we have to turn it into something that looks like this. Are there any questions about this? Is everybody convinced that this part of the code is truly equivalent to this part of the code? It's just that the second version is uglier. Yep.
So in your if condition on your what you translated to, it's always a negation of what your if is up above.
I jump around, yes. Now,
So you do it backwards, you said?
it's just, this is the easiest way to do it. This is the more efficient way to do it. You can do it the other way around. You can flip the positions of the of block 1 and block 2 and do it the other way around. But I just always kind of go the opposite. So that if the condition C is false, I go around block 1 directly to block 2 and let block 2 execute. Now the important part is if condition C is true, condition not C is going to be false, which means I will execute block 1. But after you execute block 1, you have to have an unconditional branch to L2 because otherwise it will fall through and execute block 2 as well. Is that making any sense? That we have to jump around the else block? Okay. So that's the only thing you have to really be careful about. If you have a simple conditional statement without the else, it's even easier. If the original statement is if condition C execute block 1, then you can translate that to if condition C is false, you go around to label L1. If condition C itself is false, then not false is true, then you actually execute block 1, then you fall through to label L1. Okay, is that okay so far? Kind of? Okay. Now, this condition C here cannot be, it may be a simple condition. It may be a complex, condition. In other words, it can be something as simple as what we just talked about. X is greater than 3, X equals to 3, X equals to 0, and something like that. It can also be this long, okay? X is less than Y, and, Y is less than Z, and then the whole thing in parentheses, or Z equals to 1, and blah, 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 blah. So at this point, I have not really talked about how to reduce conjunctions, disjunctions, and negations into smaller components. We'll deal with that later. Okay, but we have just talked about how to change structured programs into unstructured programs. Any questions about section 3.1? Okay. Next one is a pre-checking loop. I call this a pre-checking loop because we check the condition before we perform the operation in the loop. The general form of a while loop is like this. While condition C, and then you have a block of code to perform. The translation is to have a label before the whole thing, because when you go back, you have to go back and check the condition again. So L1 has to be before the conditional statement. The conditional statement will check to see if the condition C is false. If condition C is false, then we go around everything else and go to the exit label, which is L2. In other words, L2 is our exit label, is exit loop. L1 is loop begin. It marks the beginning of the entire loop. After we perform block 1, we also have to have an unconditional branch to go back to L1 because we have to reevaluate the condition C to see whether we can branch out or whether we can break the loop this time. Is that okay so far? Translating a structured loop in C into unstructured code using the conditional statement and just the goto. Is that okay? There's only one more. Okay, we only have to deal with 3 control structures. The last one is a post-checking loop. The post-checking loop is a post-checking loop because we are checking the condition after we perform the body of the loop. The general form in C is do, and then a block of code while condition C is true. It translates to something like this. You have to define the label L1 to mark the beginning of the loop first, followed by the block of code that you want to perform per iteration. The exit part is really easy because you just say, as long as C, if C is true, you go back to the beginning label to perform another iteration. If C is false, then it will fall through and continue with whatever statement is after the loop. Are we doing okay so far with the 3 control structures, the 3 essential control structures in C? What about switch? I can always emulate switch using a conditional statement. Okay, it's going to be a complicated conditional statement, but nonetheless, it can be reduced to a conditional statement. So that's why I don't talk about switches. And besides, the way C does switch is really broken. I don't like to use break after every single case.
Dude, break
Because
after
sometimes
every
I
single
forget.
case is awesome.
Hmm?
Break after almost every single case is awesome.
Yes, you can do some shortcuts. I don't like it.
Case A, B, C, D, E. Go here. Case F, G, H.
I'm against it. Okay, so we are done with control structures. Okay, in just 10 minutes, we're done with control structures. So what else, do we have to talk about? I mean, if that is all about control structures, what else are we going to talk about? Well, we have to kind of talk about the Boolean operators. Okay, because what if condition C is not a simple comparison? We can deal with simple comparisons pretty quickly, but what if it is not? What if it is a conjunction? If x is less than y and z equals to 2? Well, that turns out to be not too complicated either. We'll first take a look at negation. Negation is the easiest one. If the original statement looks like this, if not condition C, go to label L1, and assuming you cannot just flip the direction of the comparison or change the conditional branch itself to take care of this, you can always translate that into this chunk of code. If condition C is true, you go to L2 to continue execution. Otherwise, if condition C is false, you go to label L1. So this code here is functionally exactly the same as these 3 lines here, but I took care of the negation. Yep.
Why would you want to take that off again? Because you had it up in one of your examples above, there was a negation on C. So why would you want to?
Because we want C to be a simple comparison at some point. Now, if this is a negation and C itself is a disjunction or a conjunction or something complicated, I cannot just reverse the direction of the comparison to take care of the problem. I actually have to do something about the actual conjunction or the disjunction. Okay. So are we doing okay with the not translation? Reducing or eliminating the negation operator. The next one will take care of the disjunction or operator. If the original code is if condition C or condition D, now each one can be complicated also. Okay, so I'm just taking care of the OR operator here. If I have 2 reasons to go to label L1, if condition C is true, I go to label L1. If condition D, I go to label L1. I can just translate that into 2 consecutive statements. If C goes to go to L1, if D go to L1. Are you guys convinced that this second chunk of code will do exactly the same thing as the original code?
Yes.
Yep.
Actually, that really explains short circuit logic.
It does. And then the next one is conjunction, and it will also explain short-circuited evaluation for Boolean operators. This is it. If condition C and condition D, I go to L1. In other words, I need C and D both to be true to go to label L1. So doesn't it make sense if condition C is false, I can just give up and say, I'm not going to label L1, I'll just go to label L2, which is a continuation label. Okay? So that also explains how short-circuited evaluation works in C. If the first condition is false, you just kind of go around the whole thing and just say, I'm giving up. On the other hand, if condition C is true, I will have a chance to evaluate condition D. If condition D is confirmed to be true, then at that point, I know condition C and D are both true, and then I can go to label L1, which is the original intent of this code up here. Are we doing okay so far? With the reduction of the conjunction operator. Do we have any other operators that we have to deal with? Any other Boolean operators?
XOR?
There's no exclusive OR.
We use it all the time.
No, that's a bitwise exclusive OR. These are logical operators.
My bad, carry on.
Okay. Now I know I have some students here who took cisp310 from me. Did you at some point use the wrong operator? Accidentally use a single ampersand instead of a double ampersand? No, never.
Of course.
Wow, you guys are better programmers than I am, so I'm glad. Because you'll be the people working on the software, the firmware of my pacemaker. So I'm glad that I'm not the one writing the firmware of my pacemaker. Okay, so let's go ahead and take a look at this logic here. Okay, this is simple reduction, which basically does not involve the transformation that we talked about. Because if your condition is not x is greater than or equal to y, the easiest way to get to reverse or to get rid of the negation is to change the comparison itself. If you want to confirm that x is not greater than or equal to y, it's much simpler to say that x is less than y. Okay. The other one is something like this. If x is less than y, okay, the condition x is less than y or x is greater than y is really the same thing as saying x does not equal to y. So there are things that you can combine and you don't have to go through the mechanical process that we just talked about. So if you can do this first, okay? You can basically optimize and save yourself a few steps if you do this. If you cannot use algebra to do this, you can always go for the mechanical method that we talked about a little bit earlier. Are we doing okay so far with the translation process? How to get rid of a regular conditional statement, how to get rid of a regular loop, pre-checking, how to get rid of a regular post-checking loop, how to get rid of a negation, how to get rid of a disjunction, how to get rid of a conjunction. We are now ready to become compilers.
Yeah.
It's okay. It's not painful compared to the next homework assignment. So. Okay, so here we have some comparisons. Okay, comparisons are easy to deal with. If we have a relationship like this, okay, this is what we just talked about a little bit earlier, just presented in a different way. The R here is can be replaced by greater than, less than, equal to, not equal to, and so on and so forth. Okay, so basically I'm looking at the template and say, if I can reduce a construct all the way down to a single comparison between two things, and depending on the result of the comparison, I go to L1. How do we translate that into assembly code? As it turns out, this translates into this. Okay, so let me just read this part again using the same order of interpreting it. Jump to L1 if and only if x is blah 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 y. Blah blah blah, greater than, less than, equal to, greater than or equal to, not equal to, and so on. It's the same thing. So basically, this is the same thing that I was talking about a little bit earlier, just presented a little bit differently here. And just to be sure, I give you a concrete example, which is kind of rare. If y is less than or equal to 5, go to L1. Okay. Now, everybody should understand that when you talk about a conditional statement in C, the so-called if really should have been if and only if. Does everybody understand the difference between a if versus a if and only if? No? Okay, I can just briefly explain that, but do not let me confuse you if you don't get this part. When you say if, okay, that basically says if y is in fact less than or equal to 5, you have to go to L1. But what if y is not less than or equal to 5? The word if does not specify what to do when the condition is false. You can go to L1, that's cool. You can not go to L1, that's equally cool under the strict interpretation of what is an if. If you use if and only if, then it is becoming more restrictive. If and only if means if the condition is true, you go. If the condition is not true, you don't go. Okay? That's the difference between a if versus a if and only if. Okay? So that's why, I think in all programming languages to date, they all labeled the conditional statement incorrectly. It should have been if and only if, which is IIF or IFF instead of IF. Yep.
Having that explicit else clause on most ifs
does not help.
Negates that if this is true, do this, else or otherwise do this. Is what that else means. It means if this isn't true, if this is true, do this.
I suppose.
Otherwise do that.
But if you have a single, statement like this,
it's not our fault you're abusing C by leaving off your else clauses.
well, just a minor point. Just a minor point.
You should just have an empty else case. Else open parenthesis, semicolon close parenthesis.
Well, that's how I write programs. I always have the else case. I just put empty curly braces around it. Empty block.
Yeah.
But that's the other thing, just in case you guys did not catch the kind of conversation. When I write my conditional statements, even if there's nothing to do for the else part, I always say else and then open curly brace and close curly brace right away. In other words, to most people, I'm blowing 3 lines almost for apparently no reason.
You can compact that to 1 line and only be blowing 1 line.
No, I use all 3 lines. The reason why I do that is because just in case later on I come back and there is something to do for the else portion, I know exactly where to put that code.
I'll show you where to put that code.
Hmm?
I'll show you where to put that code.
But since I have a place for that, you don't have to show me anymore.
Aww.
Oh. Okay, but that's just programming style. If I have one single thing to do in the conditional statement, I still use the open curly brace and the closed curly brace, because just in case that later on there's one more thing to do, I don't have to worry about having to go back and use the curly braces to make it a block.
Yes. You shouldn't have blocks of code without curly braces around them.
Yeah, but when there's one thing to do, you're not required to use curly braces in the conditional statement.
Yeah, that was a big mistake.
Well, C is a programming language designed by hackers for themselves. It was never intended for students.
It was intended
Just
for
remember
lazy
that.
people.
Okay, so getting back to our example here, if y is less than or equal to 5, go to label L1. So that translates to jump to L1 if and only if y is not above or less than or equal to 5. Yep.
Can you clarify the not above?
Not above is the same as less than or equal to,
Okay.
but it is for unsigned comparison. If you want signed comparison, it becomes J and G for not greater than. Okay, so here's the easy one to remember, okay, because I'm pretty sure some of you have the question of which letter do I use for signed, which letter do I use for unsigned. Unsigned is easier, and therefore it is ABC. Okay? If it's not ABC, it is complicated. It is for signed comparison. So G, L are for signed comparison. A, B, and C are for unsigned comparison.
That's pretty clever.
I should become an elementary school teacher.
Yeah, teach assembly code to 5-year-olds.
Binary multiplication table. I will spend like 2 days to explain multiplication, and I'm done. Okay, Okay, are we doing okay so far with this? Are we ready to do something like this?
Ready for our homework assignment.
Hmm?
Ready for our next homework assignment. It's due tomorrow.
I think we are. I think we are indeed ready for the next homework
Can we
assignment.
get a few extra minutes tonight to work on it?
Hmm?
Can we get a few extra minutes tonight to work on it?
Okay, so I'm going to give you guys your next homework assignment right now, because we have just talked about all the concepts. Hello. Okay, so this is important. It's your homework. Okay, so we're gonna give you. I'm giving you your next homework assignment, and you can actually see how I create homework assignments. It's actually pretty easy. It's grading that is hard. So this grading homework assignment. I'll just call this Max 3. Okay, so Max 3 is the homework assignment. I turn it into a folder, and in Max 3, I'll give you the pseudo C code. But I'll give you the pseudo C code or pseudocode in the form of comments inside an assembly program. So this way you can interleave your code along with the C code here or pseudocode. Yes.
Are we allowed to use GCC-S?
If I see any code that only has to resemble what the compiler actually generates, I will not grade that. You can use it to inspire your code. So I know this is not the most efficient way to do it, but that's how the code is specified. So I want people to. Okay, I suppose in this case we only have to compare.
It doesn't hurt.
Doesn't hurt. Okay. Yep.
Are we being graded on making it do it that way, or on just obtaining the same results?
For this assignment, I'll just look for the end effect. Okay, so
fine.
Implement this logic in assembly language. Okay. And I'll give you the template. Okay, I will even give you all the templates. Dot data, and let's make this a little bit more interesting.
Give us some labels, X, Y, and Z.
Let's make this more interesting. I'll make X a 32-bit integer. I'll make Y a 16-bit integer, and I'll make okay. Z is the same. All right, two 16-bit and one 32-bit.
So, what's the value of X?
Hmm?
What's the value of X in? Can you set the values in hexadecimal?
Okay, obviously this is not actual assembly code, so we'll. Dot and it doesn't matter what it is. Okay, so I'll just put gibberish here because I'll explain why I put gibberish there.
Because you're allowed to change it when you grade it?
Because my script is going to change it on the fly before the breakpoint, so that way you have to make sure that you test all the possible cases to make sure your code will work in all cases. They'll all be signed, okay? Unsigned, unsigned. Unless someone want to deal with signed numbers, I think unsigned is already quite enough. So max itself, has to be a .int something because it has to be big enough to store, the result of X. And obviously, it is also going to be interpreted unsigned. Does everybody understand why I have to emphasize, all X, Y, Z, and max, they're all unsigned? I have to tell you whether it is signed or not. Because let's say for X, if I don't tell you whether it's signed or not, and it has a bit pattern of 0xFFFFFFFF, then in one case you can look at it as -1. But you can also look at it as the as the maximum unsigned value that you can represent using a 32-bit number. So I have to tell you ahead of time that everything has to be interpreted unsigned in order for you to write your program correctly. So that's why it is important to understand that everything is unsigned in this case. So getting to the text section, underscore start. I'll put a no op instruction here so that I can put a breakpoint here. Okay, tag changes the variables here. Okay.
Shouldn't that be before the no op?
Hmm?
Shouldn't that be before the no op?
Good try. Okay, and then to put a comment here, you put your code here. Okay, tag checks the result here.
Can we make that last one shorter? So we don't have to write that all out every time we want to check.
No,
the
this is
breakpoint?
already the template is given to you. This is my gift.
No, can you make that last label shorter so that it's easier to check our breakpoint, or easier to set a breakpoint every time?
You can just type tag CHE and then tab. You know what? But you can always do it, because you can add your own label in your own code, right? So that means you can put your own label L1 here. And then you can stop on your own L1 is equivalent to stopping at tag checks the result here.
I'll just put tag checks the result here in .gdb init.
Okay, so does everybody understand what you have to do for this homework assignment? Yep.
So which memory do you want to put the max value at?
The max value is going to put into the 32-bit starting at the label max. Yep.
Can we add some additional word zeros?
No. Okay. Do not change this part.
We can't.
You put your code here.
We can't change the values of X, Y, and Z attached.
Well, there are several things you can do. You can change these things to test your program, but it won't be the most effective way to test your program. What you want to do is to change the program or change the values of the memory locations right here, at the label tag changes the variables here. And I will show you guys how to do that too. Okay, so just hold on a
I've already
second.
got an idea. I'm just going to copy them into registers.
Hmm?
I'm just going to copy mine into registers.
Well, when I check the result, I have no idea which register that you are going to use to store the maximum.
EDX
So
back
you
into
will have to.
max.
Okay, let me just make sure that you understand here. Okay, tag checks the results here. Max in memory has to have the maximum value. If you put it into a register and leave the max label or the 4 bytes at max label unchanged, then my script will mark it wrong because you are supposed to put it into the memory locations starting at the max label.
Yeah, you just copy it back with them.
You
Couple
have to
of
copy it back,
Bs.
not me.
Well, yeah, that's my plan.
Okay, so let's go ahead and just do something here, just so that we can find out how to I'll just have one single comparison here, and I'll compare long x to 0 to x. Okay, just so that I have an instruction, okay, that I can affect in this program.
X will leave here. Why don't I just put a not?
Okay, that's not very interesting. 30 is good. Okay, so let me just run the program. I can show you, how you can do this part here. Okay, let me just that's not what I want to do. And I'll just have another instruction here. Compare word 40 to y. Okay. All right. One thing you want to do is to download the GDB init file that we have mentioned already in previous classes. How many people still remember the .gdb init thing?
We had a GDB.
Okay.
What do you mean remember?
You have to be able to type it out by hand for every assignment you want to use it for.
Why not just copy it into the folder?
Okay, so I'm going to cat this to .gdb init. And Okay, so you can see that I actually, you can see from here, right here, I have a function called setWord. That's something you can also use, it's a macro so that you can change a 16-bit location to a particular value. Okay, so that can come in very handy, so you don't have to go out of GDB, change the program, change the dot word definitions, then go back and check again. You can basically keep the same program and only change the values at the memory locations, and then just test the program again and again that way. Okay. All right, let's go ahead and do it. Gsteps -o max3.o max3.s ld-o max3.o gdb max3, and then we put a breakpoint at tag changes the variables here. And then we put another breakpoint at tag checks the results here. Okay. Well, see, long labels names are not a problem. It's just auto completion works. Okay, so I run the program without even doing anything, but I can make changes to x right here at this point. Now, x is a 32-bit integer, so that means you can actually use the command called set to do it. So if you look at set
can use HW watch points?
Yeah, they have a lot of set. Is it set variable? Yep. You can use set variable to do it. Set help set var. Okay, set variable can be used this way. Evaluate expression and assign result to variable var using assignment syntax appropriate for current language. So since we're using assembly programming here, the C syntax will work, but only for 32-bit integers. Okay, so you can only do this for 32-bit integers. So if I want to change the value of x, I will say set var x equals to, let's try 56. That will change the value of x to 56, because I can double check and confirm that x now has a value of 56. Is that making any sense? Other than the part that I spoke to the wrong number? That part never made any sense. Okay, so now I can also use set word, and this time I think it is y. We want to change that to, let's say 120, and that will change the value of y to 120. I can double check that, but I cannot really just do this part here. You can see that this is all wrong, and that's because when I say print y, the GDB understands everything as 32-bit integers. But y really is not a 32-bit integer. It's only a 16-bit integer. So that's why it is picking up z, is combining y and z, the 4 bytes, to mean one single integer, and that's why we are seeing a pattern that is not reflecting what y should be. There are several ways to focus on just the least significant 16 bits of the 32-bit pattern here. You can always say y ampersand 0xFFFF. Basically, you're using a bit mask to only focus on the least significant 16 bits. That's one way to do it. The other way to do it is to use the X command, examine command, which is actually a little bit more cumbersome because you're looking at a half word and you want to display it as an unsigned integer. This time you have to supply the ampersand y because you have to give it an address to examine, and it will still give you the same result. So there are two ways to examine the result, but if you want to change the content, the 16-bit content at that location, you have to use set word instead of set var, because set var will misunderstand everything as 32-bit integers, but set word is specially designed to only work with 16-bit stuff.
How about a 64-bit? If I use a system with 64-bit?
If you want to deal with 64-bit, there are no specific commands to do it. But since we are not doing 64-bit, we're good. Unless you guys want to compare 16-bit to 64-bit, that's fine with me too.
Just copy it into a register. Just copy it into a
Well, the
register.
64-bit is a little more than that. Yep. Okay, any questions? Yep.
When's this due?
This will do in a week and 2 days, so it will do next Thursday. So 1 week from the midterm on Thursday.
So we just have to get the right effect at the end. You don't care how we get it as long as it's right.
Correct.
Okay, this one will be fun and easy.
Professor Jack,
Yep.
Professor Jack, on Thursday, do we meet here first or the lab?
We will meet at the lab. So meet at the lab at 7 p.m. on Thursday.
And this
You might
is
want to
due
go
on
there
Thursday,
a little bit
right?
early.
This is due on Thursday, right?
This is due on next Thursday.
You're giving us that long to do this?
Whoever knows how to do it already knows how to do it. Whoever doesn't know not how to do it won't know how to do it.
So you may as well just give us till Thursday. I was expecting to have homework due by Thursday anyway. I was